This is the AMPERE story, and that's the title, Harnessing the Power of the Iridium Constellation for Science. And you can all see the cursor, yes? Okay, good.
Yes.
I want to make sure because I use that sometimes. And there's the name. It's a little bit tortured, but we chose AMPERE because the whole point of the project is to measure electric currents. So it kind of made sense. So, and these are members of the team, and not all of them can be here, but most of them are here. Oh, let's see. So first I want to give you the context of what the system that we're studying. This is the Earth, and this is a representation back from 1961, showing the magnetic field of the Earth, the solar wind coming in from the left. The arrows indicate the flows, and the solar wind magnetic field actually connects to the Earth's magnetic field, especially over the polar caps. And there's a convection that goes on that then returns the flow back to the day side. So there's a steady circulation that occurs. A more recent sort of taxonomy that's been discovered with many spacecraft, NASA spacecraft and others. This is what the system kind of looks like. And the Earth's magnetic field is turned into this magnetic windsock that extends way off down anti-sunward away from the sun. This distance is typically about 10 or 11 Earth radii, and it's about 40 Earth radii across and extends hundreds of Earth radii, what we call downtail. And there are a number of solar space weather hazards. So solar energetic particles have direct access to the polar caps. The Van Allen radiation belts are in this region right in here. And there are dense plasmas that cause differential charging and arcing, and those are related to plasmas coming in from these flows, and also if there's a strong compression and the magnetosphere is compressed. So that's the sort of the climate perspective taxonomy of the system. That whole system maps down to the low altitude polar regions. And there are electric currents that are related to the dissipation between this system and the Earth's ionosphere. These are called Birkeland currents or field-aligned currents, and they flow into the ionosphere, they close in the ionosphere, and then flow back out in these pairs. And these currents lead to thermospheric heating or upwelling of the upper atmosphere, which leads to orbit decay and drag. And they also lead to ionospheric irregularities, which disrupt communications and GPS navigation. And on the ground, they actually produce geomagnetically induced currents, which lead to power grid effects and actually increase erosion in pipelines. So there is a number of practical implications for this system. But let's take a look at
these contamination for our satellites.
Huh?
It's also contamination for our satellites' attitude control systems.
We can get to that in the question and answer. There was a fascinating exchange of emails that went on early on in the project. Yeah. So, but this is what the Birkeland currents look like. They're upward over in the evening and downward in the morning. And then the red shows how those currents close in the ionosphere, looking down from over the polar cap. This is what the magnetic perturbations would look like. The actual system has an extra set of currents here, where there's a downward and an upward pair, and then a downward and an upward pair over in the morning. And most of the closure is actually between them. What that means is that the magnetic perturbations look like this. You don't see anything equatorward of this system, and when you're in between these currents, you see a large signal and then a small signal over the polar cap. That's actually been known since the late 1960s, that this would be the case. Now, geomagnetic storms, which are related to solar storms, they are produced by solar storms and the coronal mass ejections from those. Typically, as I said, the magnetopause is at sunward about 11 RE, but during storms, it can be compressed well inside geosynchronous orbit. And that leads to 100 times decrease in the volume of the magnetosphere. The roll zone expands to below 50 degrees. That's about an 8 times increase in the polar cap area. And the electric potential that's imposed on the system can get over 100 kilovolts, and the total current can be increased by about 5 times, and that leads to about a 50 times increase in the total amount of power going into the upper atmosphere, and it's localized. So this is why these things are important for satellites and spacecraft charging and ground effects, and these changes occur rapidly. In less than 30 minutes, which is less than about a third of a low Earth orbit satellite period. and that's important. Now, the geomagnetically induced currents, among other things, they have significant effects because they're a DC current that gets imposed in the power grid, and the power grid is not designed to handle DC currents. And these things do cause significant grounding currents where the systems and the transformers are not designed to handle that kind of DC current. Leads to inefficiencies, and there can be some significant consequences. Where you decrease the lifetime of equipment, you can have localized disruptions. Severe storms can lead to significant disruptions in larger power grids, and they could even lead to failures of large transformers, and those have very long lead times, so that's potentially very serious consequences. So we need to understand the storm time system. So that's what we wanted to do, was to see if we could find a way to predict what the storm time system would do. We knew what the statistics were like. We knew this from satellites in the 1960s. They increased in intensity as things became somewhat more active. And we thought, well, so the storm time system is easy. We just scale this up. That should be pretty straightforward. There's no hard work here. Well, I started to look at this in the 90s, and this is what the magnetic perturbations looked like from the upper atmosphere research satellite. It does not look anything like what I was showing you earlier that you expect to see from low Earth orbiting satellites. It is totally crazy. There are multiple peaks. There are structures within the structures. They aren't necessarily symmetric, and they do very strange things. This is an animation that shows an equatorial view of the magnetosphere. There's a compression coming. Notice the clock and how things change. This shows the pressure. This shows the electric currents, and this is a meridional view of the pressure. Actually, this is the magnetic field. The compression has happened, and notice how rapidly these field line currents, which are shown here in red and blue, how rapidly they change in the northern and the southern hemisphere, and they aren't the same in the northern and the southern hemisphere. And what this tells you is that the storm time system is not anything like the statistical system. It's much faster and it's much different. So in sum, we need a bigger boat. We need something that can measure this system rapidly enough so we can characterize it. And that's where Iridium came in, because this is what the constellation looks like. This is the system you're trying to measure. It is the perfect coverage to characterize this system globally. So that's what got me excited about it. So how did this get started? Well, back in 1995 in Baltimore, we had finished a scientific meeting, and I was in conversation with a gentleman by the name of David Klumpar. He was with Lockheed at the time, and Lockheed was building the Generation 1 Iridium satellites. And he knew an engineer who was working on it, and he confirmed that all of them had magnetometers. I thought, well, that's awesome, but they were body mounted, and we had no idea what the downlink plan was. But there were 70 satellites, and the orbits were perfect, so I was pretty excited about that. So I called an Iridium engineering contact I got from David, and that person no longer worked for them. And he said, well, try this guy. So I emailed that person, and I got an email and a phone number. I called him. He actually answered the phone, and he actually worked for Iridium. Ah, this is great. So this is for a science project. Right. You're a student or something. Oh, a PhD scientist at Hopkins. Oh, okay. I'll ask. Okay, so that's sort of how it got started. Well, time went by. Another follow-up email to the effect that I actually intended to submit the idea to NSF for study funds. So understand, I haven't actually seen the data. I haven't actually talked with anybody who would tell me that I could get the data. But, when you're desperate, you submit the proposal anyway. So that's what I did. I submitted the proposal having never seen the data. And they actually, I asked for 80K for 3 years. They actually gave me some money, which was amazing. So I sent another follow-up email to Iridium, and I have some funding to study this now from the National Science Foundation. So there was some more name dropping that went on. Anyway, so then the phone rang. And what happened was, apparently that engineer was at one of the Iridium meetings. This was before the launches. And he said, well, one of our executives and I were at a meeting, and the executive asked, isn't there some science we could do with Iridium? And said executive might be listening today. I don't know. And my email had just come. So then he said, you wanted mag data. And so they sent me some mag data from the engineering telemetry. And I was enough so that I could demonstrate that it could work. This is data from the Defense Meteorology Satellite Program, and you can see these are the perturbations you sort of expect to see, you know, one way and on one side and over the polar cap like this. This is Northern Hemisphere and then Southern Hemisphere. But the sampling we had from Iridium was once every 200 seconds because it was housekeeping telemetry. And you can see it completely misses things now and then. That's awfully coarse. But I was able to show that if you could increase the data rate by 10 times, the resolution of the magnetometers was good enough to actually do the job. And there were times when, for engineering purposes, they were sampling more often. And this is actual Block 1 engineering data where I've time shifted things so that the latitudes are the same. And you can see we are seeing the signals that we expect to see. And it was this kind of analysis that convinced me that we could make this work. And that's when Ken and I started to get together and put our heads together to figure out how do we do this. It was at that point when I did some of those briefings. You all took an interest in it and you found a way to do it. And this is my graphic for sort of a poor man's understanding of that. There's an enormous spacecraft health and telemetry packet. There was from Block 1. And the magnetometer samples were a tiny bit of that. And it was simply impossible to increase the rate of this health and telemetry packet. But what you figured out you could do was to use something called an event response message, which was designed for the satellite to basically phone home and say, I need help. But instead use that to pack data in it and then push the samples. And it turns out there were actually, I think, 74 that you settled on for number of samples in an event response message. This could be done, but it required flight software changes. So getting somebody to pay for that was the difficult part. We tried to propose it to NASA. That was dropped for various reasons. We were trying it again in 2001. Turns out that opportunity was canceled because the administration decided to go a different direction. There was a mission of opportunity for NASA. We tried that, but the science wasn't closely enough related to the mission. So then I briefed NSF in 2006. Notice the timescale here. They requested a proposal in 2007. So that was awesome. So I submitted the proposal. AMPERE was selected for funding. I was told that they got some of the highest reviews they'd ever had on a proposal for this. So on the 14th of January, 2008, I was serving as a magnetometer scientist for Messenger, and that was the day that we had our first flyby of the planet Mercury. And it was so exciting because we were going to see the other half of the planet. But the other thing that happened that same day was that the NSF contracts officer called to question the large sum contract to, at that time, Boeing Services Company, with the news that NSF does not allow a fee for engineering services, period. And I thought, yeah, right, Boeing is going to waive profit for this piddly little thing. I don't think so. And so this was the challenge we had, you know. And so it was a good day and a terrible day at the same time. So Ken and I had actually we got to put our heads together, and we spent several months working with you all to restructure the subcontract as a data buy, and to set the price per bit below the transmission cost for the Iridium satellites. So we did that. So this is a conversation that actually happened. We had a telecon with NSF, and they said, well, we regret that NSF will not be able to do this. And I said, oh, what if we just purchased the data? So there was no subcontract. And he said, you mean there would not be a subcontract for engineering services? Correct, just a purchase contract for the data. I said, well, as long as you can demonstrate that the price is fair and reasonable, that would be fine. And I said, okay, how soon can we send you a revised cost proposal? And that's how it actually happened. It came within 10 seconds of being not happening during that conversation. Long story short, its funding started in 2008. The software changes were made, and test data started in 2009, and the AMPERE data officially started, well, in June, but actually it started in January of 2010. And this is the AMPERE overview. These are the satellites. This is a graphic Ken put together where the transmission occurs to the ground network, over the satellite network and to the ground. That's one path, and the other path is when there's a store and dump, and this is used to sort of fill things in, and then the data is a data accounting, and then it's sent to us, where we do the rest of the satellite processing That's how the system basically worked then, and that's how it continues to work today on NEXT. So this is what we do. We take the raw magnetic field data, and then there's a lot of processing that Audrey is very familiar with, and Ken, to derive these small perturbations. And these are small. These are like a tenth to at most 1% of the background field. If you were to plot the background field, you would not see these. But when you process them and reduce them, this is data from the entire constellation for a 10-minute interval. It's the first time we ever got a view of what the system looked like in as short a time as 10 minutes. We've never been able to do that before. Different colors are different satellites, and you can see you get the system, but there's all this other interesting structure that shows up in there. Anyway, we fit this, we take this, and we apply Ampere's law, appropriately enough, to derive the currents, where blue is downward and red is upward. And you can see we are getting the pattern that we were showing earlier, if you get for that. This is a movie of a storm in 2015, known as the St. Patrick's Day storm. There was actually another one 2 years later. And you can see the different satellites going across. Some of them have higher data rates, and here you can see things just starting, and then the storm really expands. And this is the sort of thing we had never seen before. We had never been able to watch how this system actually behaved. And you can see there's all kinds of interesting departures from that simple statistical system. Asymmetries, east and west. It's much more equatorward on the evening side than it is in the morning side. There's all kinds of structure in these currents that we had no idea was there before. We had hints, but we couldn't prove it, and we couldn't study it, that's for sure. So that's what, and we have those movies for everything. The other thing that we did is we took these field line currents. This is for a different storm, 2011. The green dots are locations of ground magnetometer stations, and then the lines are indicating the magnetic perturbations and the direction of the currents associated with those. Completely independent data measurements. And what you can see is that when the currents are changing, the magnetometers on the ground are responding, and they're responding in concert with the overhead current. So that's telling you very clearly these signals and these systems are responding to the same physical system, and they're giving you complementary views of what that system is doing. And there's been a lot of work putting these different data sets together to put together a consistent picture of the overall system. We also were able to do comparisons with theoretical simulations. So this is a particular storm on August 5th. The black trace is the total integrated current. So if you take those currents and you integrate it, and you get millions of amperes, and I said it got up to 20 million amperes during storms, and there it is. And the black is what we get from Ampere, which would be considered truth. The red is the statistical model. The blue is one physics-based simulation. The green is another one, and the brown is another one. And the basic conclusion is that none of them really get it right. And that was the first time we were able to really have something that we could say, now that's the truth. This is what you should be measuring. That's not what your model is giving you. And that prompted people to go off and make some changes. Actually, things are worse than it looks like in those time series, because these are the instantaneous pictures of any of the models, and that's what Ampere is showing you. And the first time I showed this at a meeting, I wish I'd have had a camera there to capture the winces on people's faces, because they realized, oh my gosh, we're not doing a very good job. Well, we've gotten better. We've gotten a lot better. This is a model that's run where you actually have to couple the magnetosphere and the ionosphere in a time dynamic system. This is that particular time frame. That is what this model is giving you. Now you're getting somewhere. That is starting to really zero in on what the system is doing. So it really has advanced our ability to predict what the system is doing. It's one of the key things we needed to do. People have been doing science with this like crazy. This is just a smattering of some of the publications that have been done. This could go on for at least three more pages of scientific papers that have been published based on the Ampere data. So it's been a huge success, and NSF is just super excited about it. The other thing that's exciting is we've got it working on NEXT. We've got the processing working on NEXT. Ken and Audrey and I have been working really hard for the last 3-4 years on understanding the magnetic signatures in the NEXT data and figuring out how to correct for it. And it's been just a great adventure sorting that out. And the next data are actually better. So this is the processing that we have to do, just so you understand how the sausage is made. You start out with the raw magnetic field measurements. That's what you see here. You add a model field to that, which is pretty close, but there are some differences. You take those differences. Now let's zoom in on those differences. So this is what it looks like. Oh my, how do I get this? Well, let's do a calibration fit to it. Oh, okay. Oh, there's a square wave. Oh, we know what that is. Ken and I figured out what that was. Let's subtract that off. Well, the battery is doing something. Okay, let's subtract off what the battery current signature is. Now let's zoom in a little more. What have we got here? What's this orbit period signature? Oh, well, there's coolers on the star cameras. Oh, okay. Well, let's subtract that off. What's all this fuzz on here? Oh, there's another square wave. Ken found that one, by the way. And well, now there's all this fuzz, and then we figured out how to remove that. It turns out it's related to rapid power draws. Finally, we get to the point where the Birkeland current signatures are standing out well above the noise level in the next data. So that's how the sausage for Iridium Next, that's how we make it. And Audrey and company and we have been working really hard to show that this could actually work for the world magnetic model. Here's the noise level from the Block 1 or the original generation of satellites, and this is Next. Same scales. You can see we're doing about a factor or 2 better in terms of noise. We're getting down to the digitization level of the mags, which is pretty impressive. So here's a movie from Next. And what you can see is there's more samples, and the data is actually better behaved because the baselines are so much better because the attitude system is superior to what we had. But it's working on Next. These movies are out there for all of the data that we have that we've processed for that, and the community is using it, and they're really excited about it. The other thing we can do with this is that we can actually track Earth's background magnetic field. This shows the residuals in the total background magnetic field as measured from AMPERE on very quiet days for, I believe this is the radial component, these are, and different days, individual days. This is a model from the swarm satellites. And you can see they're seeing the same thing. And if anything, there's a little more structure in the results from the Iridium constellation as there are in the state-of-the-art models. This is what prompted the U.S. government to say we should plan on using Iridium to do the world magnetic model, which is used in your cell phones and all sorts of other things. So AMPERE has a really bright future. The community is using it like crazy. We've released products from Next. We're working on this interval from 2017 to 2019. It was a lot of work, but it was worth the wait. And we're doing the implementation of the Iridium Next magnetic field processing for the world magnetic model. And NOAA and the U.S. Space Force are interested in understanding how they might use the real-time capability that AMPERE can provide for some of their space weather monitoring and situational awareness. And we have to prove that it's useful for them, but I know that it'll work. But that's another road of convincing the sponsor that yes, it's worth your investment to do this, and we'll get there. Thank you very much.